Hi guys, it's Chloe here. I wanted to welcome you to the first lecture video for the calculus division. For you guys who don't know, my name is Chloe Maideche and I am the head tutor for the Maths Forum, and I'm also one of the tutors in calculus with Anne Fleischer and Paul. Um, so this introductory video draws a lot from the YouTube video that I linked for you guys. So those of you who watched it, it might be a bit repetitive. For those of you who haven't got a chance to watch it, it might be something new, so I encourage you to just really focus. So the content of this video might seem a little bit abstract, but the introductory part is really just to get you guys to have a really good idea of calculus and the methods behind it. Because I think one of the most dangerous things you can do, or one of the worst ways to learn calculus, is to think about it as just a set of rules that you must apply. Because you will learn rules and you will learn important things that you must remember, but calculus is so much more than that. Calculus, it's a way of solving problems that we don't know how to solve, but framing them in a way that we do know how to solve to get a better understanding of the problem and get closer to the solution to it. So it's really important that you grasp where calculus comes from and what you're trying to do here, so you can apply it properly and have a good understanding of it. And in future study of calculus, you have a very good grounding for it. So guys, the first concept we're going to think of is the rule of first principles. And we're going to do this by thinking of a story about how it was derived. So first we're going to think about what calculus really means. So firstly, calculus is an abbreviation, and it's an abbreviation for infinitesimal calculus. So infinitesimal calculus. And infinitesimal just means infinitely small, or it's talking about infinites, but in this case we're thinking about infinitely small values. But in traditional colloquialism and within the maths world, we tend to just drop the infinitesimal part and just talk about calculus. So calculus, the root word, is actually the same root word that we think of when we think of calculators. So calculus itself is actually Latin for small pebbles. So you might be wondering, small pebbles. Some of you might be wondering what small pebbles has to do with math. So if you remember in the ancient Roman days when they used an abacus, small pebbles made up the part of the abacus when the abacus was divided, or the abacus divided the small pebbles into rows and columns, and they used that to write. So for them, calculus is really synonymous with math. And from that, you can think of just how important calculus is to the math world, when calculus really just means maths or calculate. Okay, so where does calculus come from? Two thinkers, Gottfried Leibniz and Isaac Newton. Now, Leibniz and Newton both came up with the same way of solving the problem simultaneously at the exact same time in two different places. So first you have Isaac Newton, who was thinking about the problem and solved it, and he was in England. That was the first one. And the second one was Gottfried Leibniz, who also was thinking about the same problem and came up with the exact same solution as Newton, all the way in Germany. And what's famous about this is neither of these two collaborated, and they came up with the exact same. They found the exact same problem and came up with the exact same solution at the same time. And there was much debate between the two of them about who actually came up with the solution first, but it seemed that they did so simultaneously. Now, Isaac Newton has gone on to be very famous across the world, and so a lot of you probably would be familiar with his name, whereas Gottfried Leibniz is less known, but in terms of calculus, they're both equally equated as sort of the fathers of calculus and solving the problem. Okay, you can stop it. I'm going to focus on this guy, Isaac Newton, and what happened to him. Or sorry, how he came up with the idea of calculus. So it's a story. Let's tell a story. Many of you remember, famously, that Isaac Newton was sitting under a tree and an apple fell on his head. There's much debate about whether it was actually an apple or it fell on his head, but the concept is the same. An apple fell. And there Isaac Newton he's sitting there under the tree, and this apple falls. And he's wondering to himself, okay, this apple's fallen on me, and it's clearly gravity, Gravity is making this get pushed down, it falls down on me, cool. But then he was wondering, as he was sitting down under the tree, he could see the moon. And he's wondering to himself, the moon is kept up in place, and the moon is kept up in place by gravity. But this apple is pushed down and falls by the same force, that is gravity. So he's wondering to himself, what is happening with gravity? How come gravity can have the same force, can make an apple fall, but hold the moon up? They're so far apart from each other, the distance is so great, and there's just two completely different consequences of the force. So Isaac did something quite clever. So he's thinking about solving a problem that he can't solve, right? An unsolvable, unknowable problem, or one for which he has very little knowledge of. And he's trying to think of it in terms of something that he does know about, right? And that's sort of where we're going to go with calculus, trying to solve something we don't know much about and we don't know how to solve, but using the things we do know and manipulating them and thinking about them cleverly to try and solve the problem. So let's think about gravity. So Newton noticed something that he thought to be quite strange about gravity. And what he noticed is that if we think of this sort of as a poor graph of gravity, and we have distance on the x-axis and force, probably measured in Newton meters, of gravity. What he noticed is that gravity, or the force of gravity on the y-axis, is inversely proportional with the distance between the object that it exerts that force upon. In other words, as you move along the x-axis, or you move further away, it's really the square distance that's important. So if you move in terms of the square of the distance as you move further along, the force of gravity becomes weaker, or the rate of the force decreases. So this presents the first problem for Newton, more namely that along this function, the rate of change is no longer constant. So this problem may not be so obvious, but let's think about it in terms of what we already know, what we're already familiar with. And let's think about a straight line, right? We all know the formula for a straight line. So if we wanted to find the rate of change or at a point or along the graph, we already have a formula for it. All we need to do is get 2 points in the graph, right? And then along those 2 points, we just look at the rise and compare it to the run, right? So we just look at rise over run. And that's a formula that you guys will be familiar with already. That is what we call gradient. Now, all we need to do is look at the change along the x-axis, the change along the y-axis, compare the two values, and then we will know the gradient of the function. And that's fine because we can take 2 points here, we can take 2 points here, we can take 2 points here. Anywhere along, we can find the gradient easily by comparing 2 points. Now, the key reason we can do that is because along this entire function, we have constant gradient. Now, this is a very important problem. You must remember, if we want to describe the key areas of maths in one word, so say if you think about geometry, and you want to think about that as sort of space and shapes, if you want to think about algebra and you want to think about it in terms of the relation between values, so say x and y, or other variables and how they're related, if you're thinking about calculus, what you're thinking about is change, the way things change. That is the fundamental idea of what you're trying to find out by calculus. And so it's a very big problem when you have a function, or to Newton, he was representing a very big problem trying to understand how gravity works. We've got a function that changes at different points all along the curve, all along the function, at every single distance. So something moves further away, the rate of change of gravity changes. Whereas if it was just gravity was described by a straight line, like we're familiar with, at any single point, the rate of change is constant, and we can calculate that rate of change by merely comparing 2 points and looking at the rise over the run. You can stop there. Newton has a problem. He needs to calculate the gradient at each point on a function where the gradient isn't constant. So, we recall, if you want to find out the gradient of the function, what you're really thinking about is the steepness. if you know the steepness of a function, that steepness is its gradient. So he needs to know the gradient of a function, or the steepness of the function at any point. So what that means, so what he really needs to know is the gradient of the tangent at that point. So this is the tangent at that point. So what Newton's trying to calculate is he realizes I need to find the gradient of a tangent at that point. But the problem, as we've looked here, when we think of gradient, how we calculate gradient is by comparing 2 points. But by definition, the problem with a tangent is tangents are tangential. Tangent is actually a Latin word that has the same root as the word tangible. And tangible just means touching something. And so tangent just means it touches the function at 1 point. And so if you need 2 points to calculate gradient, and a tangent only touches the function at 1 point, we clearly have a problem. So now Newton needs to find a way to solve this problem. Okay, you can stop. So Newton has, again, a very ingenious solution to this problem. So if you recall, our problem is that we have a tangent. We need to find the gradient of the tangent, but we only have 1 point. So Newton thinks about this, and he thinks, actually, a clever way to think about this would be in terms of a circle. So let's think about a circle, right? So here you've got a circle. And this is actually where the idea of the tangent comes from. So if you've got a point here on the circle, and you've got a tangent to the circle. Oops, let me redo that tangent. Sorry guys, my drawing skills aren't amazing. If we redo the circle here, and we think that we have a tangent there. So, Newton's solution. If we think about the circle, sorry for the poor drawing of the circle, and we think about this line, the tangent to the circle. So Newton has an ingenious plan. We don't know the tangent of the circle, but what we do know, what we can think about, is a secant to the circle. A parallel secant to the tangent. And remember, the key feature of something being parallel is they share the same gradient. So you think of, we've got a secant to the circle here, and we're just drawing secants that are parallel, approaching the tangent. And what we notice is that the chord to the circle of the secant, remember the chord is the line that's within the circle, right? And the secant just crosses through the circle. If you look at the chords to the circle, as they approach the tangent, they get infinitely smaller. Until eventually, which obviously I can't draw, they get infinitesimally smaller until the chord is actually not a chord, it's a point. And that point is the point of tangency. So recall, what we're doing is we're talking about chords as they approximately approach and get infinitesimally smaller to the tangent point. So we didn't really have a language for approximately smaller or approximately coming towards in Newton's time. So Newton had to think of a way of describing chords as they get infinitesimally smaller and approach as close as possible to the chord, right? And the length of the chords is length h, and you'll see why that's important just now. And so when we think of the way of approximating as this length h tends towards 0, is we think of the idea of limits, right? Limits, right? And more importantly, we think of the limit as the distance h tends to 0. You know, how does the function behave, or how do these chords behave, how does the gradient of the tangent behave as this distance, right? Or at the limit as this distance h tends towards 0. Okay guys, this is the part where you really need to focus, because this is the part that probably what Newton's most famous for in terms of the first principles in calculus. This is the part where we take everything put together, or everything we've seen so far, and we put it together into something very useful, very applicable. So what we do is instead of thinking about circles now we're going to start thinking about the graph, but the exact same logic applies. So now let's think of a curve. Obviously you would see that this curve is not the same curve as the curve of gravity that I've drawn this way. It's actually a reflection of the curve, but that's not too important. So if you look at this curve now, and you think of 2 points, right? And these 2 points are sort of the edges, right, of the chord, like we've seen in the circle. So if you had to imagine this being all the way around as a circle, right, you see the chords. Now let's imagine that this point is x. Well, first, let's imagine this graph is defined by the function f of x. Let's just assume that that's the name of the function, f of x. So now this point here, the first point we're going to call x, and we're going to imagine the distance between these 2 points is h, right? So now this is x, right? Then the x value, right, or the x coordinate of this point necessarily has to be x plus h, right? And the y value of this point at x, right? If the function's f of x and you've got the point x, then clearly the y value is just f of x, right? And so the coordinate of this point will be x, f of x, right? And for this point, if this point is x plus h, and the function is f of x, then clearly the y value of this point is going to be f of x plus h, right? That's the y value. So the coordinates of this point then will be x plus h and f of x plus h, right? That'll be the coordinates of that value, of that point, sorry. So we're trying to do the same thing, right? We're trying to see at some point in between these two points, x and x plus h, trying to find the tangent at some point here. We're trying to find the equation of the tangent at some point there. And to do that, we need to identify what happens as h tends to 0. We're trying to find the gradient of the tangent, right? As this chord gets as close to possible, as the distance between these 2 points gets as close to 0 as possible. And we find the gradient of the tangent at that point. So we're looking at what happens as h tends towards 0. We're assessing the gradient of the tangent at the limit as h tends towards 0, right? Or the limit h of 0. So what we have to do is think of gradient, right? And if you remember, the formula for gradient is rise over run, right? So rise and run is the formula for the gradient. And what we need to do is to plug it in exactly the same way, right? Nothing different. So we start with rise. What would be the rise here? Well, the rise would be the difference between the two y values, which in this case is f of x plus h, and it would be minus the y value here, which is f of x, right? So that would correspond to the rise. Now what would be the run? Well, that would just be the x distance between the 2 points. And we've necessarily defined that here as h. So it will all just be over h. But we want to assess this gradient, right, at the limit, right? We want to assess it with the limit of h is 0, right? But clearly, we can't the h is never 0, right? Clearly h is never 0 because this function is undefined. So we can't directly assess the function at 0. But if we think of, the way we work with limits, so we can't assess the limit at h equals 0 directly. In other words, you can't just plug in 0 here, right? Obviously, this function becomes undefined. And so, what we do, I want you to think about what you've done with limits before. And let's think of the function, right? X squared minus 25 over x minus 5. And I want you to assess the function. Clearly, x cannot be 5. There's an asymptote at x equals 5 in this function. So to assess the function, we can assess the limit of the function, right, at the point x is 5, right? So clearly, x cannot be 5, right? But we can assess what happens at the function at the limit, so where x is 5. So how do we do that? If you recall, we factorize, right, or expand, right? And we see x minus 5 is here, cancel out, and what we left is x plus 5. So now, if we plug in the value x equals to 5, what we're going to be left with here is 10. So what does that mean? Well, what it means is, from above and below, the function tends towards 10. It doesn't reach the value of 10 at the point x is 5 because the function is undefined. There's an asymptote there. But the function tends towards, from above and below, 10. And you can draw this function and work it out yourself, and you'll see that the function tends towards 10 from above and below. So it doesn't actually arrive at 10, but it tends towards 10. In other words, since the function is undefined at 5, we cannot know what happens at 5. The function is undefined. But we can use what we do know here to work out what would happen to the function as it approaches 5, as it gets infinitesimally close towards 5. Right, so that's very important. And we're going to apply the same framework and the same logic to assessing the limit of f of x plus h minus f of x over h, right, as h tends towards 0, or at the limit h 0. In other words, what we're saying is the gradient of the tangent is equal to f of x plus h minus f of x at h assessed at the limit as h tends to 0, the limit h at 0. So recall, it never actually, h never is 0, but we look at the gradient of the tangent by looking at this function at the point as h tends towards 0, as it gets infinitely close to 0. Now, what you realize, and what we've realized, is that the gradient of the tangent, or the idea of rise of a run, is not an ideal way to look. It's not an adequate way to think about this. Because there really isn't a run, right? We're looking at h tends as close to 0 as possible, right? As both the rise and the run, the distance between the 2 points is as close to 0 as possible. So we're not really looking at the rise and the run. Now, you'll know from physical science, some of you will know that when you denote the change in something, right, you use a sort of delta, right? So we're going to use this as that sort of delta, as the change. So instead of thinking about it as rise or run, or the gradient or m of the tangent, as you usually would, we're going to think about it as the change in y over the change in x, dy dx, right? The rate of change. And that, right, as some of you will be familiar with, but, let me write it out just so it's a bit neater for you guys. So that dy by dx, right? There we're looking at the change in y over the change in x, right? So the change in y over the change in x as h tends to 0. So we're not thinking of rise and run per se, we're thinking of change in y over change in x, and that is the denotation for the derivative of the function, right? The derivative of y with respect to x, right? So this function is saying f with respect to x, right? That's how the function is derived. So you're finding a value y, right, with respect to x. Here we're finding the change in y with respect to the change in x, right? So this notation is equivalent to writing f dash of x, or sometimes simply f dashed. So sometimes you would find if the function was described as sort of g of x, or h of x, or c of x, whatever variable, you'd keep the variable there, and the dash of the x will ascribe to the derivative, or just the dash. If you're thinking, say, in terms of velocity, or some other force, or any other concept that require two different variables besides y and x, say you're looking at speed and time, or something, or if you're denoting the speed as something moves at a particular time, or the weight of someone at a particular time, or anything like that, or the value of money at a particular time, you might use a different notation here as opposed to dy dx. It'll be the same concept. So, you know, if instead of f of x, say the function was f of t, and you're thinking of the value, where say maybe y represents the value of your money in your bank account at a particular point of time, then instead of dy by dx, because you're no longer thinking of the change in y over the change in x, now you'd be thinking of the change in y over the change in t, was a change in time. So instead of dy dx, you'd write dy dt, right? So all you need to think of is the change, right, in the y-axis, right? The change in what the function is using is what's being explained by the function, right? Or the dependent variable in this case, so say the money, right? And over the change in the independent variable, or in this case time, right? The variable that some of you might know as the explanatory variable, right? What is using to explain the other variable. So if you just remember that, that's how the notation will be struck. So that is very important. And so because of that, right, because of that, we can put this back, get the h back, and instead of writing m of the tangent, right, we're going to write f dash of x is equal to the limit as h tends to 0, right? There, this little formula here, this is what's known as the calculus so here we replace the gradient of a tangent with f dash of x, as I explained in the notation, which is just the equivalent of dy by dx, which is just the change in y over the change in x, right? So the ratio, if you want, of the change in y with respect to the change in x, or this whole formula f dash of x, which is equal to f of x plus h minus f of x over h, assessed at the limit as h tends to 0, or the limit of h0. This is what we know as the first principles. This is what is known as the first principles of calculus. So that is all known as the first principle of calculus. Basically what we're saying is, if you want to know the change in y with respect to the change in x, what we call the derivative of the function, or f dash of x, if you want to assess that, what you do is you find the f of x plus h minus f of x over h assessed as the limit of h tends to 0. So if you wanted to find the derivative of the function f of x squared, instead of f of x, or f of x plus h, you'd be f of x squared minus f of x squared, if that makes sense. So it'd be f of x plus h all squared minus fx squared over h, assessed at the limit h tends to 0. That's how you do it. So basically, the first principles is one way of deriving the derivative of a function. If you do all of this properly, you will get the derivative of the function. Okay, now I know for a lot of you, and for me as well when I was learning for the first time, the concept of first principles can be quite daunting, like where it comes from, putting it together, but it's important to know it. It's important to know where it comes from to understand what you're actually trying to do. The actual application of the rule is far more easier. But before we go through an example and showing you how to use first principles, I want to teach you the one rule that you'll need to know from your matric syllabus, which is the power rule. The power rule is a much quicker way of deriving the derivative, by far quicker. The only problem is the power rule tells you nothing about what you're trying to calculate. It doesn't tell you where it comes from anything, as first principles does. But the power rule is by far the more effective way of using it. So the question doesn't ask you to derive using first principles, and you need to find the derivative of the function. It's much easier to just use the power rule. Now the power rule is as follows. But before I show it to you, remember what I said at the beginning. It's important not to think of calculus as a set of rules that you apply, right? It's important to know where we come from and where and why we're doing what we're doing. That's why I started by explaining first principles, as opposed to just teaching you the rules. Because it's important to know where we're going with this. So the power rule is a very useful rule, and it says the following. If you have a function f of x equals to x of a. Ooh, sorry, the x was quite poor. But we have a function f of x equal to x to the power a. What the power rule tells us is that f dashed of x is going to be equal to a x a minus 1. Right? Very simple. So an example would be, if you had the function f of 2x, or f of 2x squared rather, let's do it like that, then f dashed of x would simply be a, right, brought forward, so 2 times the 2 that's already in front, x, and instead of a, got 2 minus 1, or a minus 1. So you've seen the same thing here. What we've done is we brought the a down, and here we brought the 2 down, yeah, so it's now 2 times 2, and you've said a minus 1, and here we've got 2 minus 1. So the answer is quite simply 4x. So, as you can see, it's a much quicker, much easier way of deriving the derivative, but it doesn't really tell you anything about what derivatives are, right? But it's a very easy way of telling what the derivative is. And we can use this to check first principles. So now that you know the power rule, we're going to use it to check our answer when we derive something from first principles. So we've got the power rule, we see how it goes, and for simplicity, we'll use the same function here, 2x squared, because we already know the derivative is 4x. So now let us derive that derivative from first principles. So I wrote down 1 as the power rule, but we're going to work with 2 as first principles. But often it's taught the other way around. I just wanted to do it that way so we can see the way of checking our answer. So 2. So we have a function f of x equal to 2x squared, as we said already. Now we're going to find what f dash of x is. And we're going to find it by assessing the limit as h tends to 0, or at the limit as h tends to 0. We're going to assess f of x plus h minus f of x all over h. So, it's important for notation's sake that f dash of x stays like this, and until you substitute h for, or you substitute 0 for h, you've got to keep writing the limit as h tends to 0. Because until you've got rid of h, until you've substituted 0 for h, you are still assessing this at the limit h tends to 0. So we carry on. So we've got the limit as h tends to 0, and now we've got the function 2x squared as opposed to f of x. So now what we're thinking of is 2 of x plus h all squared. So remember, what does the function f of x tell you? It tells you every time you see an x, what do you do with it to derive your y? So in this case, for every x we see, we take 2 and the value of that x squared, right? So now we've got f of x plus h. Instead of an x, we replace it with an h. So we've now got 2 of x plus h all squared. And now we minus 2x squared. Oh my goodness, sorry. Minus 2x squared, not squiggly, all over h. And then we're going with it. So you get the limit as h tends to 0, and we expand. So we know that x plus h all squared, we know how to expand those. So we know we're going to find x squared, so we're going to have 2x squared. We know it's going to be x times h times 2, so 2xh, right? And then we times by the 2 on the outside, so we're going to have plus 4xh. And we know we're going to have h squared, but it's 2 on the outside, so it's 2h squared, right? Plus 2h squared, and we're going to minus 2x squared, and it's still going to be all over h, right? So we can do some cross cancellation here, or just, simple cancellation. And we're going to see that the 2x squared terms cancel out. So we're just left with 4xh plus 2h all over h. Now, what can we see? 2h squared. what we can see here is we've got a common h. Right? You can see there's a common h here. So we're still assessing it at the limit of h to 0. We haven't substituted 0 for the h here, so we're still assessing it at the limit. And so like I said, there's a common h, so we're still assessing at the limit, and a common h that we can remove. So we actually here we can take out a common 2h. Take out a 2h, and what we're left with is 2x plus h all over h. So what we can do is cross cancel the h's, and we're still assessing the limit. We haven't quite replaced 0 for h yet, so we're still assessing at the limit, and what we're left with is 4x plus 2h. Now we don't have anything over h, so we can substitute h for 0. And so we're no longer assessing at the limit, because we are now substituting 0 for h, and now we are at the limit. So we write that f dash of x is now equal to 4x plus 2 times 0, which is just 4x. And if you recall from the previous example, or if we use the power rule, we've got the exact same answer. I want to do it here just to refresh your memory. We have 2x squared, and so we go 2 times 2, x 2 minus 1, and so, so we left with 4x. So we can see that from first principles, we are able to derive the derivative of the function. And that's important, this can come up in your exam, to derive a function from first principles. So some key things to remember is you do not drop the term limit as h to 0 until you've substituted 0 for h. Very important, because you're assessing this function at that limit. If you drop that before you substituted 0, then what you're writing is incorrect, because you're no longer saying you're assessing this function at the limit h tends to 0. So yeah, that's very important. And another way of thinking about f dash of x is thinking that f of x just dictates a function. And when you think about the derivative, or the rate of change, it's always different at every single point. So it's changing. So you're saying you're describing how the rate of change changes as the x value changes. So it's a function of x, but it's f dash because it's a function that doesn't tell you the value of x, but it tells you the value of the rate of change of x. That's why it's f dash of x, the derivative of the function. So yeah, you follow the steps, you manipulate your 2x squared term into x plus h. So you substitute instead of x, you're now considering f of x plus h, and you minus f of x over h. You do